Okay, in this chapter, we cover gases and some of their basic properties. Okay, so how many gases can you name? So most people don't know many gases. Probably know more solids and liquids than gases, and that's simply probably because there's not as many gases exist as there are solids and liquids, and most things tend to exist as a solid or a liquid and not as a gas. Okay, so let's see how many gases you can name. So what are the top 10 gases in the atmosphere and air? Okay, so pause the video and see if you can name all 10. Did you pause it? No, I didn't think so. But if you did pause it, thanks for playing along. Okay, so let's see. So what are some 10 gases? Let's see if you can come up with 10 gases. So did you come up with 10 gases? So the top 10 gases in the atmosphere, number 1 would be nitrogen gas. So nitrogen exists as a diatomic species, N2. So it's 98.08% of the atmosphere. So based on chapter 10, we could have come up with the Lewis dot structure for N2, right? It's nitrogen, nitrogen, triple bond. So most of the air you're breathing right now, about 78% of the air you're breathing is nitrogen gas. Okay, so the second most abundant gas in the atmosphere would be, hopefully you said O2, oxygen. So about 21% of the air you're breathing right now is oxygen gas. And so oxygen, of course, is another diatomic gas. If you drew a Lewis dot structure, you would come up with the molecule looking like that, with the double bond between the two oxygens. Third most abundant gas in the atmosphere is argon. It's 0.934% of the atmosphere that you're breathing. So it's a monoatomic species, so it's just individual atoms of argon floating around in the atmosphere. And so if you notice, those three gases alone are about 99.9% of the atmosphere. And all of the other gases are just available in very trace amounts. Okay, so some other gases. So column 8 in the periodic table are called the noble gases, right? Why are they called gases? Because they're all solids, liquids, or no, they're all gases, right? So some of the other noble gases are in the top 10. Neon is number 5. It's 0.001818% of the atmosphere. Number 8 is krypton. It's in the top 10. And other noble gases, xenon is not in the top 10. Helium is in the top 10. Helium is number 6. Of course, what do we use helium for? Well, one thing that we use it for is blow up balloons at a party. But it's only 0.000524% of the atmosphere. Okay, so some other gases. Carbon dioxide is number 4. CO2, right? Carbon double bonded to 2 oxygens. CO2 gas is 0.039% of the atmosphere. Number 7, livestock produces a bunch of this, and that would be methane gas. Methane is CH4. Right, volcanic activity produces a lot of methane gas as well. Number 9 is hydrogen gas, H2. And number 10 is N2O. If you remember how to name a molecule like that, it's dinitrogen monoxide. Also sometimes called NOS. This is a gas maybe you're familiar with. It's also called laughing gas. So that's the top 10 gases in the atmosphere. Most people probably cannot name 10 different gases. Yeah, I had a professor once tell me that he did not think that there would ever be another gas discovered, simply because most gases, as we'll see later in this one of these lectures, most things tend to be solids or liquids because of what we covered in chapter 11, because of intermolecular attractions. And once intermolecular attractions become strong enough, then a molecule exists as a liquid or a solid instead. But some other common gases that maybe you thought of: xenon, carbon monoxide is a toxic, deadly gas. Ozone, which you find in the upper atmosphere. You have an ozone layer that helps protect the Earth. HCl, you've worked with hydrochloric acid probably in lab before. Technically it's a gas. If you work with it in lab, then you're working with it dissolved in water as an aqueous solution. acetylene is maybe a gas you've heard of before. Right, that's acetylene. Where is it used at? It's used in welding because it burns at a very high temperature. Flame of a acetylene torch is about 2,800 degrees Celsius. Okay, so just in case you're curious, so Mars atmosphere. So Mars atmosphere is 95.32% carbon dioxide. And the nitrogen gas is number 2 in the atmosphere, 2.7. Nitrogen gas is 2.7% of the atmosphere. Argon gas, 1.6%, and oxygen gas is only 0.13% of the atmosphere on Mars. So if you ever watch much science or news these days, there's a lot of interest in people talking about trying to explore Mars these days. Obviously, there's lots of technical difficulties to overcome them. One is simply the miles, the distance between Earth and Mars, but this will be another very technical difficulty to overcome. Oh my gosh. So we're accustomed to breathing air that's about 21% oxygen. If you go to Mars though, the air is only 0.13% oxygen, so, and 95% CO2, so obviously you can't just breathe the air on Mars because you would suffocate from it. So there's not enough oxygen in the air, so you have to have a artificial respirator in order to breathe on Mars. Okay, so if you're going to study gases, then one thing that you have to study or learn and understand is pressure, because gases exert pressure. So what is pressure? It's a force per unit area. So there are several different units of pressure that are used. Atmosphere, 1 atmosphere is 760 millimeters of mercury, which is 1.01325 bar. A bar is a unit of pressure. One that maybe you're familiar with is PSI, so 14.696. 1 atmosphere is 14.696 PSI. What does PSI stand for? It stands for pounds per square inch. So you probably deal with PSI if you've ever aired up the tire on a bicycle or your car. And then that is equal to 101,325 pascals, which is the SI unit of pressure. So one thing that you have to do in this chapter all the time is convert between the different units of pressure. And then another unit of pressure that is used is a torr. 1 millimeter of mercury is equal to 1 torr. So anybody who's ever worked on cars maybe used torque wrenches. Okay, so those are different units of pressure, so that's just something that you get to do in this chapter, but you'll always be given conversion factors, but you'll have to know how to convert between one unit of pressure and another. Okay, so how do you measure, maybe you've ever heard of atmospheric pressure. If you ever watch the news, the Weather Channel, they talk about atmospheric pressure all the time. So how do you measure atmospheric pressure? You use an instrument called a barometer. So let's go through basically how a barometer works, how you can measure atmospheric pressure. So if you did this experiment in San Diego or Galveston on the Gulf Coast, so basically you're at sea level. So if you did an experiment like this, if you took a test tube and then you fill with mercury, and then you invert that test tube into a beaker, but you do it instantaneously so that you don't spill drop. Okay, so now you have a test tube full of mercury turned upside down in the beaker. So what would you expect to happen in the very next instant? Well, you would expect gravity to come into play. So what's going to happen in the next instant? is some of this mercury is going to start coming out of the test tube. So would you expect all of the mercury to come out of the test tube, or only a little bit of it? Well, so what you would find if you were doing this experiment is that all of the mercury doesn't come out of the test tube. Some of it stays in the test tube, and some of it comes out into the beaker. So you would think maybe all of it should come out of the test tube because of gravity. You would think it maybe would come down to an equal level, but it doesn't. So if some mercury stays up in the test tube, then something must be forcing it to stay up in the test tube. And so what is that force? Let's draw this sucker a little bit bigger. So that force would be atmospheric pressure. So what's above the surface of the liquid is air, column of air. And what is air? Well, we just saw that air is a bunch of things. It's all of these different molecules. Those are the top 10 air molecules in the air, but there are other air molecules as well. So all of this is in the air. So you have some nitrogen, and some oxygen, some argon, some helium, some neon, a lot of nitrogen. 78% of this air is nitrogen, right? 21% is oxygen. So all kinds of different air molecules. And they exert pressure. How do they exert pressure? Because they're moving. One, because they have weight. Air molecules have mass, right? If we take nitrogen gas, for example, 1 mole of nitrogen molecules would weigh 28 grams, so they have mass. And so gravity works on them too. Right, we should hope that gravity works on air molecules, otherwise we wouldn't have an atmosphere. They would all escape into space. All of the molecules would. So, but they're all moving around, and they have mass, and they're going to hit the surface of the mercury, and that's going to exert a force, which is basically going to help keep some of the mercury suspended in the test tube. Okay, so what we want to do now is let's measure that distance. If we measure the distance, how much, so if we did this experiment in San Diego, so we're at sea level. So what you would find is that column of mercury is 760 millimeters of mercury high. So there's enough air pressure at sea level to suspend 760 millimeters of mercury in a small test tube like that. Or there's 1 atmosphere of pressure. So that's basically how you measure atmospheric pressure using an instrument such as a barometer. Okay, so now let's say you did the same experiment in Denver, Colorado. So you went from the ocean in Galveston or San Diego, and you went to Denver, Colorado. So Denver, Colorado, is in the mountains, so it's at a higher altitude. What's the altitude of Denver? Well, if any of you are sports fans and you watch professional football, Denver Broncos, they play in Mile High Stadium. Why is their football stadium called Mile High Stadium? Because Denver is about a mile high in altitude, so about 5,280 feet in altitude. Okay, so if we did the same experiment in Denver, and you measured that column of mercury, would you expect it to be the same, 760 millimeters high, or did you expect it to be taller or shorter? And the point to recognize here is because you went up in altitude, then the column of air above the surface of the mercury liquid is now shorter, so it's going to exert less force. So there's less atmospheric pressure. So yeah, in Denver, Colorado, that column of air would only be, where is that? It would be 626 millimeters of mercury high. So less atmospheric pressure in Denver than in San Diego because of less air molecules. Okay, so in this chapter there are several equations that you have to know how to use. One is what's known as Dalton's law of partial pressure. So this basically says the pressure total so the total pressure in a mixture of gases is equal to the sum of each gas's pressure. So gases basically behave independently of each other, so you can just take the pressure of each gas in the mixture, add them up, and that will be the total pressure of the system. Okay, so at sea level, so let's just take an example of how you could apply this. So at sea level, atmospheric pressure is 760 millimeters of mercury. So what is the pressure of oxygen gas at sea level? Well, so the way that you can solve this is so that we know oxygen gas is 20.946% of the atmosphere, so oxygen is going to exert 20.946% of the pressure. So we can just take the 760 millimeters of mercury total pressure and times the fraction that is oxygen. So oxygen pressure would be 159.2 millimeters of mercury at sea level. So what would it be in Denver? So the pressure of O2 would equal well, so in Denver we said the atmospheric pressure, total pressure, is 626 millimeters of mercury. And the atmosphere is pretty consistent throughout the entire Earth, so it's still going to be 20.946% oxygen in Denver as it is at San Diego, approximately. So in Denver, then the pressure of oxygen would only be 131.1 millimeters of mercury. So this has consequences. At one place it would have consequences in athletics, right? So what's the comparison? So if we took 131.1 millimeters of mercury in Denver, divided by what you get at sea level, and that's 0.823, so only 82.3% of the atmosphere in Denver is what you would have at sea level. So the oxygen in Denver is only 82% to what you would experience at sea level. So this has consequences, of course, to athletes. If you take like the San Diego Chargers and they're going to play the Denver Broncos, and San Diego travels to Denver to play, then what you might see is the San Diego players on the sidelines when they're not playing with an oxygen mask on, trying to get more oxygen into their system because they're used to breathing with every single breath 159.2 millimeters of mercury, but now they're competing in air that only has 131.1 millimeters of mercury, so their body's not used to that, so they're going to have a little bit harder time getting the oxygen that they need. So one way to compensate for that would be to have oxygen mask on the sideline. Another way that athletes may compensate would be to travel to the site a few days in advance, right? And let your body acclimate to those conditions so that you get more accustomed to breathing air that's got less oxygen in it. Okay, so just because I find it interesting, a few other examples of these applications of gas laws. So if we take Earth and space, so the Earth-space boundary is about 62 miles. And so there's about 5 times 10 to the 8 kilograms of air molecules in the atmosphere. But about 75% of the Earth atmosphere is concentrated within the first 6.8 miles from the first surface of the Earth. So why might that be the case? Why is there more? So the air is more dense. At lower altitudes, as we just saw, the atmospheric pressure is only 626 millimeters of mercury in Denver, which is only 1 mile in altitude, versus 760. It's 82% of the atmosphere if you go 1 mile in altitude. So why is it more dense at lower altitude and less dense at higher altitudes? Well, because of gravity. Because gravity works on air molecules just like everything else. And so the heavier molecules are going to be more concentrated towards the surface, and the lighter air molecules will be more concentrated at higher altitudes just because they have lower mass. Okay, so of course as you go below the Earth's surface, so if you went to the Dead Sea, then as you go below the Earth's surface, then pressure would increase above what you would get at sea level. So at the Dead Sea, the atmospheric pressure then is 15.48 psi. Okay, so again, as you go up in altitude, so we looked at Denver. What if you went to Mount Everest? So Mount Everest is 5.5 miles in altitude. So there's, of course, interest in people like to hike Mount Everest. So it's 5.5 miles in altitude. And so at that altitude, there's only 4.89 psi. So that's only about 33% of the air. That's what you would get at sea level. If you fly on a commercial airline, commercial airlines fly at about 7.5 miles in altitude. At that altitude, there is only 0.19, so about 19% of the atmosphere. So how is it that you're able to fly and still breathe on a commercial airline if you're only getting 19% of the air that you're accustomed to breathing? That would be, of course, because airlines have their cabins pressurized to about 10.9 psi. So that's about at 74%. So a little bit, it's pressurized to be a little bit more than a mile high in altitude, where you get about 74% of the atmosphere. And so if you've ever flown, you probably experienced your ears popping. As you go up in altitude, the pressure decreases, so air is going to be coming out of your eardrum, and then as you descend and land, maybe if you've ever flown, experienced pain in your ear because then pressure is increasing, so air is trying to get back into your ear. And if you're congested, that can create problems. So if you ever wanted to climb Mount Everest, so I like to discuss this just because I think it ties in nicely with this gas law chapter. So if you ever wanted to climb Mount Everest, first thing you do is fly to Kathmandu, and then you'd trek to this place called Lukla, and then you would hike up to what's called base camp, which is about 3.3 miles in altitude. So Mount Everest is 5.5 miles. You would climb to about 3.3 miles at altitude. That may take you about 8 to 10 days to hike that. And so that may cost you about, I looked it up once, about $1,500 plus airfare to get to base camp. And then once you were there, you would stay at base camp for 40 to 60 days. So that's a long time. So why would you just hang out at base camp for 40 to 60 days? To let your body acclimate to being at such a high altitude where there's such low oxygen in the air, of course. And then if you're adventurous enough and wanted to finish the climb, so not only do you have the atmospheric conditions, the low amount of gases in the air to worry about, so only 19% of the oxygen to breathe. There's hurricane force winds at Mount Everest. It's always frozen. On a good day, from what I've read, it's about negative 15 degrees Celsius on a warm day. And breathing can lead to just breathing can lead to exhaustion because you're taking in about 20 to 30 breaths every single minute. You know, why are you breathing so much? Of course, to try to get more oxygen into your system because you're only getting 19% of the oxygen with every breath that you take. Okay, and just one more example of gas laws in sports. So if you're a baseball or softball fan, so where is it easier to hit a home run at? In San Diego or Denver? Well, so San Diego tends to be a pitcher's park. And place in high altitude tend to be hitter's park because if you hit a ball, it's going to travel further in Denver than at San Diego. Why is it going to do that? Because there's only 82% of the air molecules in the air, and so whenever the baseball hits an air molecule, that creates friction, and it's going to slow the ball down. So if there's less air molecules, then the ball is going to travel farther. So where could a pitcher, I can't spell here. So where can a pitcher throw a curveball better? It would be in San Diego, because if you know how to throw a curveball, you have to put spin on the ball, and the ball's going to basically experience friction with the air molecules, and that's going to create a pressure differential, which will help the ball curve. Or where could a pitcher throw a fastball faster? Well, that would be at high altitude. So if you're a fastball pitcher, you'd probably prefer to pitch at a high altitude because there's less air molecules. That's going to slow the ball down, so your pitch should travel faster. Whereas if you're a curveball pitcher, you probably might want to prefer to pitch at a low altitude where there's more air molecules to generate friction on the ball and help it curve more. So same would apply with soccer, football. If you kick a soccer ball with the same force, where is it going to travel further? In San Diego or Denver, and that would be in Denver, again, because there's less air molecules in the air to cause friction with the ball, so the ball is going to travel further, kicked with the same force. Okay.